Hello everyone and welcome to episode 2 of Microman, entitled Rise of the Superbugs, with my guest host, Superbugs. If you're a Dragon Ball Z fan, my cert will actually make a lot of sense to you, especially as the video proceeds, which explains this isn't even my final form. Superbugs are actually what the mass media depict as highly resistant bacteria, which are resistant to a lot of antibiotics. I actually chose to do this episode a little bit ahead of schedule instead of the previous episode, which I had planned, because of the fact that my mom's birthday was just a few days ago, and because of the fact that antibiotic resistant bacteria would ultimately lead to her passing. I decided to devote this video to her and tell you all about antibiotic resistance, why it's important, and why it's a major threat. I will be doing a future video to go into more details about antibiotics and how they work. But the focus of today's episode specifically is on antibiotic resistance. But to start things off, I wanted to give you a little bit of understanding of antibiotics themselves. Antibiotics were discovered by Alexander Fleming in 1928. Fleming was actually a microbiologist, and he was growing some bacteria when he noticed that there was a clearing on the petri dishes of the bacteria who's growing, because some mold spores managed to blow and get into the dish, and resulting in a large area where the bacteria were not able to grow. He eventually came to find out that this was the antibiotic known as penicillin, which would become the first antibiotic to be officially discovered. Penicillin was eventually mass-produced, and it was actually became critical in World War II, where it was used to treat wounded soldiers. However, just with the rise of antibiotics, so would come antibiotic resistance, which would soon turn to be a problem. Over time, a lot more antibiotics were discovered, synthesized. However, with it, antibiotic resistance came hand in hand. Antibiotics were actually isolated from several different sources and have continued to be isolated from different sources over time. These sources include fungus and molds, such as Alexander Fleming discovering penicillin, which is actually produced by a kind of mold. There are other kinds of mold and fungus which also produce antibiotics. In antibiotics that were discovered that are produced in bacteria. In this case, it's a lot more about competition. So the bacteria produce antibiotics that may only target certain kinds of bacteria, essentially killing off the competition so that it can get a lot more nutrients. There are other natural sources which have not been well characterized. These include antibiotics from plants and other species. Lastly, another major source of antibiotics has actually become those that are produced in labs. Specifically, antibiotics that were already discovered are being modified to either A, counter resistance, or B, make them stronger. There are antibiotics that are actually being discovered within the lab itself. This is actually done by taking a lot of different chemicals and trying them out to see which ones are capable of killing the bacteria. So this is called compound screening, and this is actually similar to work that I produced before starting at UC Irvine. So next I wanted to illustrate a very important point, as not too many people actually know what exactly a bacteria and a virus is. This is something that I will be talking about a lot more in a future video. However, I did actually make a simplified diagram to kind of explain. So right here, you kind of have the typical animal cell right here. So it's pretty huge in comparison with its nucleus where all the DNA is stored. Bacteria, on the other hand, are a lot smaller. And then there's viruses, which are even smaller than them. There also are a special kind of virus called phage. And these kinds of viruses are viruses that specifically attack bacteria. So antibiotics only work on bacteria. Antibiotics only kill bacteria. These do not affect viruses and generally don't affect our own cells. Because viruses, when they are able to produce an infection, they are able to implant their DNA and they begin to grow inside of our own cells. This includes things like the cold virus and the flu virus. Antibiotics won't target these, so taking antibiotics, you're not going to kill this, your cold, your flu will go on. However, it will kill bacteria. The reason why this is important to know is because of the fact that there are both good and bad bacteria. And when you take antibiotics, you are essentially targeting both the good and the bad. So it can have adverse reactions. Improper antibiotic regimens, so pretty much when you take the antibiotics and you don't follow instructions or you take them at the wrong time, this can actually give rise and help create even more of resistant superbacteria. This is an overly enlarged bacterial cell right here. So within the bacterial cell, you have its bacterial DNA, which is one loop that's all kind of squiggled around, as well as like various bacterial machinery with it. So antibiotics are basically broken down into two different kinds. So antibiotics that are bacteriostatic specifically inhibit the bacteria and they prevent it from replicating, from really doing much of anything. This buys your own immune system, your own body, it buys it time to call in the cavalry and like all its reinforcements and like start attacking the bacteria, like bam, 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 and like doing its job and getting rid of the bacteria themselves. This is how bacteriostatic antibiotics work. Then you have bactericidal, which, as I kind of mentioned, these work by directly killing the bacteria. So now we get into the heart of the discussion where I'm going to start telling you about what antibiotic resistance is. So you might ask, what actually is resistance? Specifically, resistance is when the bacteria are able to find some kind of means to stop the antibiotic. This could be by either reducing the effectiveness of the antibiotic or by preventing the antibiotic from working at all. One simplified example is by a small mutation. So to simplify things, DNA is used to make machines known as proteins. So these proteins are composed of a bunch of amino acids and they're built up so that ultimately they have a shape. So this shape is actually really important because antibiotics, in often cases, are targeted to the specific shape of the bacterial protein. So as you can see, it fits right in here. However, sometimes just the slightest mutation will keep the machinery, or the bacterial protein, it will keep it functional. However, it will alter the shape so that the antibiotic is no longer able to get into its target. So this is one simplified example of what bacterial resistance is. So now I'm going to talk to you about the origins of antibiotic resistance. So there actually is natural resistance that occurs because of the fact that bacteria are naturally kind of warring in their own environment. However, a lot of the antibiotic resistance is actually selected by. start to get desperate, like, and they try to do desperate, like to try everything, like trying to find some means of like countering it. So in this case, they're actually being pressured to succeed, just as you're being pressured to do well in your exam. The selection actually does occur is because of improper treatment and abuse. So abuse is kind of what I was going over earlier. It's like when people take antibiotics because for all kinds of reasons. It's like, I have a cough, pop some antibiotics. It's like, I have the flu, pop antibiotics. So this is abuse. You're taking antibiotics at all kinds of improper times, and this is helping to lead to resistance because the bacteria in your own body start to see all these antibiotics, and a lot of your bacteria that live inside of you, like they start dying. But some of them may have something that allows them to live. So you're killing all of its neighbors, but then one single bacteria may survive because it may possess a trait that is necessary for its survival. So this single bacteria then starts multiplying, and then pretty soon all of this bacteria is taking over, like, say, your intestines, and they're all resistant to whatever antibiotic you were like abusing or whatever. The reason why this is important is sometimes when bacteria become desperate, they start to scavenge and they start to pick up things from the environment. And say that, like, the good bacteria that's living inside you, it drops some DNA. It's a bad bacteria that suddenly comes in invade, may go and pick up that DNA, and then bam, it's resistant. I will go over that in a minute. So another major source is improper treatment. So when I say improper treatment is that I'm sure that you've been prescribed antibiotics in the past. And it says to take it for maybe like 10 days, 14 days, maybe a week, maybe 3 weeks. But you start to feel better maybe after like 2-3 days, so you stop taking the antibiotics. Bad move. Because you are just killing the bacteria that are highly susceptible. Meaning that all of the weak bacteria die off real quick. But you stop taking it, and the strong bacteria, they're left. And then they start to take over. So this is why it's really important when you are taking antibiotics, take them as prescribed. If you're supposed to take 2 a day for 14 days, do exactly that. Take it for the whole course. I don't care how it makes you feel. If you take antibiotics, you need to make sure that you empty that bottle because of the fact that this is one of the key ways of how resistance is rising. That combined with abuse, like taking antibiotics whenever you don't need them, these two are major sources that are contributing to the rise of antibiotic resistance. So as I said, to help with this, only take antibiotics if they're prescribed by your doctor. Number 2, take them as prescribed. Don't just take them for 3 days and when you feel better, stop. If you have to empty the entire bottle, take it. So these are the ways that you can help. So sometimes you may actually be prescribed antibiotics for preventative treatment. Like often in case you go to the dentist, you get a tooth pulled, it's like they prescribe antibiotics because they don't want your tooth to become infected because there are bacteria in your mouth and you may eat bacteria. Once again, you have to take them as prescribed. However, preventative treatment does actually come with a risk, which is why doctors never prescribe antibiotics as a preventative means unless they consider you at high risk for infection. Like this is like after surgery, maybe after you have a tooth pulled. But if you just take them like on a daily basis trying to prevent yourself from getting sick, that's also a recipe for disaster. But one of the biggest recipes for disaster is farming practices. Once again, antibiotics are used as preventative means, but in this case, they are fed to the farm animals. They're put into their feed and everything. However, oftentimes like this feed gets washed away and or something may happen and it starts to get into the ground. It gets into the groundwater, then it gets into the rivers, and it's like bam, you have low levels of antibiotics just floating around. So you might ask, low levels of antibiotics, what harm they could do? Well, I'll give you an analogy. So imagine you're trying something like really, really hard for the first time. Like say you go to the gym and you're going to do like a bench press. You're going to lift your weights. And it's like, you do not start off with like say 200 pounds. Like you start off right at the beginning. Well, if you start off just the beginning, what happens? You start to get stronger, and over time, you can lift more and more. So this is how resistance works. It's like you give the bacteria low levels of antibiotics, it starts to help them get stronger and stronger. Another example is, say that you're randomly attacked and you get stabbed. Like say you get stabbed like just once, like here. You know, you get stabbed once, it's like, if it hits something major, you may die. But you could, on the other hand, it may miss or whatever, and you live to see another day. On the other hand, the more times you get stabbed, the better the chance of something actually happening to you. So, yeah, like a whole bunch of times, like greater chances that you're going to die. Well, once again, bringing it to bacteria analogy, is like they see an antibiotic here, an antibiotic there. Like some of them may have a greater chance to live. On the other hand, when you're actively taking them, it's like coming in with multiple knives and like killing it, or whatever means of action the antibiotic is doing. But when it's in the environment, it's like a single knife is just like floating around here and there. So it's like it may give the bacteria a chance to live. Thus, how resistance comes to be. When bacteria are under pressure, they start to become desperate and find some kind of means for countering these antibiotics. You can think of it like going to the beach and bringing a metal detector. Like you sit there, you scan the sand, you know, like doing your thing, and chances are you're mostly going to find junk. Like you'll find a bottle cap here, like another piece of garbage, maybe like a soda can, you know, like all worthless stuff. So this same thing the bacteria are doing when they're becoming desperate. They're searching their environment and looking for anything that can help them fight the antibiotics. Once in a while, they'll find something good. Like if you're at the beach, it's like, you might say, ooh, a gold coin, or like, oh, a silver dollar, you know, something of interest, you know, something of value. Same thing with the bacteria. It's like they say, ooh, a resistance gene. So it's like, bam, they find something in the environment and they're able to resist like a couple of antibiotics. It's like, you know, it may help, may not, but they find it. And then they're able to take this, what they find in the environment, and they use it to help fight against the antibiotics. However, once in a while, like you're at the beach and it's like, you may get like super lucky. It's like very rare chance, but you may get super lucky and like find a whole treasure chest, you know? And it's like, look at this, may have like jewels and weapons and all kinds of stuff. Now, not just gold coins. So the reason I mentioned weapons is because of the fact that this is exactly what can happen with resistance. It's like the bacteria is scavenging and they won't find not just something to resist the antibiotics, but something that may actually make them stronger. So we have our harmless little bacteria here, and then it goes and it finds this resistance gene. And then it takes this resistance gene, and then, so this is its DNA, and it's this little extra DNA just floating around. But sometimes it finds a treasure chest, and this extra DNA may not only help it become resistant, but may make it stronger. So bacteria don't actually have spikes, but it's kind of an example. It's like bacteria is now stronger. It's like super spiky bacteria or superbacteria. Now, welcome to Bacteria Resistance 101, and this is your teacher, Super C officially. So yeah, now I'm going to be talking about the methods of how bacteria are capable of resisting antibiotics. So the first method that bacteria can employ is by raising a shield. It's like, bam, you're not going to get me. So they put up a shield. Or they may just find other kinds of means of just blocking the antibiotic from getting into the bacteria itself. Because if the antibiotic can't get in, bam. Like some bacteria are naturally able to do this because they have not just one, but they have two cell walls. So the antibiotic would ultimately have to pass through two walls to get in. However, the bacteria can do something else. Like they can find ways of maybe, so to speak, making their walls thicker. It's a little bit more complicated than this, but essentially imagine adding an extra layer to the wall. So now the antibiotic has to travel even further. So it may have trouble getting in, may block the entrance. So the second method is here depicted, like this is pretty close, a very simplified version of penicillin, a common antibiotic. So a second way that the bacteria are able to resist is it has natural proteins or enzymes, which it may only express when needed, or just it may find from the environment, like different ways of resistance. So what these enzymes do is they can target the antibiotic and change it. So suddenly, bam, it's like it's no longer the same shape anymore, so it's not going to work because it modifies it. So now the antibiotic won't work anymore. Ta-da! So the third way I've already kind of gone over is just by modifying its own protein so that the antibiotic is no longer able to interact. As I said, it binds a square, it binds a circle, and no more antibiotic resistance. However, antibiotics do have one way that is especially problematic and is actually rather common with a lot of extensive antibiotic resistance cases. And this is, it creates a pump. So here's your antibiotic goes in, but it then has a pump. It's like, kicks it right out. So imagine you take antibiotics, they go in, the bacteria starts pumping them out. It's like, so it gets rid of these. So these are some of the very simplified methods of how bacteria can counter antibiotics. So as I mentioned, a lot of these things aren't actually natural. So the bacteria, well, natural perhaps not the best word, but they aren't natural to that bacteria. Like they may exist in a different bacteria, but they become desperate, they get DNA, and suddenly they develop this technique themselves. They're essentially training. Or they like go with the metal detectors, like, ooh, treasure. So they find these methods, they become resistant, and then you have a problem. Do you know why? Because now you have drug resistant or antibiotic resistant bacteria. Most bacteria, or better to say, most pathogenic bacteria have some level of resistance at this point. There was a recent article that actually cited that resistance is quite rampant because they did swabs of like the New York City subway system, and they found resistance genes were like everywhere. So resistance is here, and there's nothing we can do about it at this point. However, it's not just there, but it's getting worse. Why is it getting worse? Because of the rise of multidrug resistance. So when resistance comes, it may resist like a couple of antibiotics here and there. However, there are times when it's able to resist multiple antibiotics at the same time. Sometimes these may all be antibiotics that are all very similar to each other, and sometimes it's like antibiotics that may have all target like the same machine or the same protein or whatever. And sometimes it's able to just generate these pumps and just kick out everything that is detected as foreign. Or not everything, but a whole specific, anything that looks close enough, it's like kick it out. Because it figures that these aren't its own. So what this is actually is called multidrug resistance. So one such example of this is known as the NDM1 plasmid. This is some DNA that is found in the environment. It stands for New Delhi M1, that's the name of the plasmid. And a lot of bacteria are able to pick this up from their environment. It's actually become quite prominent in India, which is how it actually got its name. So from this, it's actually able to resist all kinds of a specific kind of antibiotic. So as I mentioned, penicillin, which is actually, its kind of antibiotic is called the beta-lactam. So this one essentially allows it to resist all beta-lactam antibiotics for the most part. However, this is just one such example, and this is only the beginning, because bacteria are very smart, so to speak. I guess it's better to say resourceful, because of the fact that bacteria came here first, and we're just guests in their homes. So because of this, they keep on finding new ways of resisting. So some bacteria have been put under so much pressure because of what we've been doing that they've become extensively multi-drug resistant. Another such example is, some of you may have heard of MRSA, methicillin-resistant Staph aureus. It is specifically what actually took my mom from me. However, as MRSA is already highly drug resistant, however, it has a worse form, which is called Visa, which then progresses into Versa. Versa is actually even worse. It's extensively multi-drug resistant, standing for vancomycin-resistant Staph aureus. But it's actually resistant to most known antibiotics. So it is a huge problem. Like MRSA itself was already quite drug resistant, but Versa is even worse. And it's borderline of what is called the last kind of resistance, which is called pan resistance. Pan resistance is when bacteria are resistant to all known antibiotics. And if you think that this is not going to happen or is not a threat, you're wrong. It's already here. So there's currently only a couple of pan-resistant bacteria that exist right now. And usually people who even come in contact with these are quarantined because it is such a big threat, because these bacteria are not able to be killed by anything, by no known antibiotics. Or the only treatment may be antibiotics that are so severe, so harsh, they actually harm us. And normally these aren't even prescribed because they do more harm to us than they do the bacteria. Or they do equal harm to both. But in the case of when something which is resistant to everything, it's like they may not have a choice. It's either that or let the bacterial infection just live on and on, because you can't kill it anymore. One such example is there's a pan-resistant strain of the sexually transmitted disease gonorrhea. This gonorrhea is unkillable, but there are more threats than just that. You may have also heard of tuberculosis. Tuberculosis has gone through the cycle. It was drug resistant, then multi-drug resistant, extensive drug resistant, and recently in India, there has been the rise of a pan-resistant form of tuberculosis, meaning that you can no longer kill this bacteria either. So as you can see, bacterial resistance is becoming a major problem and is a major threat to the world right now. So right now, a lot of scientific research is actually being focused on cancer research because of the fact that cancer is a major killer. In fact, it is one of the leading killers in the world right now. And just like bacteria, it can develop resistance to its own drugs. However, an interesting article actually cites that bacteria are a continuing and emerging threat. And by the year 2050, so this is about 35 years, bacteria may become the #1 killer in the world once again, just like they used to be back in the old days before we discovered antibiotics, surpassing cancer. So, as I said, multi-drug resistance is on the rise, pan resistance is on the rise, and bacteria are just getting stronger. So because of the fact that it is on the rise, is part of the reason why I want to study bacteria and help find new cures and treatments for this growing and emerging threat. So I'm not living in the present where cancer is the major threat. I'm thinking of the future where bacteria will become the #1 threat in the world. So to continue, I wanted to discuss a couple of other aspects. So I wanted to conclude the video by discussing the future of resistance and antibiotics now and how it will evolve in the future. So as I said, by 2050, bacteria will become the #1 killer once again, surpassing cancer. It is an emerging threat. However, yeah, the future is kind of bleak, and honestly, it will get worse before it gets better. Part of the reason is because of the problem of antibiotics. So currently and in the future, a lot of the new antibiotics that are being developed towards a narrow range. So meaning that they will only target a specific kind of bacteria, or maybe even only specific bacteria themselves. Like the bacteria that causes stomach ulcers, H. pylori, they are developing antibiotics that specifically kill this bacteria. So when the advantage of developing narrow range is that if you're only targeting one kind of bacteria, you're not helping to breed resistance by killing and targeting a whole bunch of others. However, the biggest problem with developing new antibiotics is actually funding. So you have to think of it from a business perspective. So major drug companies are trying to make money because ultimately when you're running a business, that's what you want to do. You want to make money. And antibiotics aren't money makers. Do you want to know why? So a lot of drugs that are being developed are treatments because so people may end up having to take this for the rest of their lives sometimes. So even if they have to do that, just imagine the money keeps rolling in, rolling in. So the companies are able to benefit and they're able to develop new drugs, etc. So because of that, it allows the companies to develop even newer things and new treatments and such. So there's a lot of money in treatment. However, there isn't money in antibiotics because antibiotics, you're not treating the infection. More or less, you're killing, more or less, you're leading to its death, either directly or indirectly. So if you you take something for a couple of weeks, and suddenly your target's dead. There isn't very much money there. And the reason why is because of the fact that you won't be able to sell very much of this if somebody's only able to take it 2 weeks. Even if you start an outrageous amount, you're still killing off the very thing that you would need to even take this medicine for. And developing drugs actually is expensive. Like, I work in a laboratory, so I can actually tell you this. I've actually run experiments like, this is just one kind of experiment, just to answer one small question in a bigger question. And this single experiment has cost, what is it, like $5,000. And that's just a small question as part of a larger question. But when you're developing drugs, it costs an outrageous amount because you have to go and you have to run trials, because you can't just feed it to bacteria, which is fairly cheap to grow, but you have to test in humans, make sure it's not harming the people, not killing, not producing much of side effects. And running human trials, and not to mention all the equipment, everything that you need, this costs a lot of money. So developing new antibiotics can go up into the millions of dollars. And research is actually quite expensive. Very expensive. So that's the major problem with developing new antibiotics. So a lot of the research being conducted on bacteria, instead of being conducted by these big pharmaceutical companies, is actually being conducted in a lot of small academic labs, like often like those seen at your local university. And transitioning this into the larger pharmaceuticals is not exactly the easiest thing. So the only thing these labs can do is they try to get more funding. And it's important also that the government is able to fund this and recognize that this is an important emerging threat. An alternative approach that some labs are actually investigating is, well, there's actually a couple of alternatives. One of them is that I previously mentioned there are a specific kind of virus known as phage, which targets bacteria. And there are some labs which are investigating the potential use of phage as an alternative method, instead of antibiotics, of targeting and treating bacterial infection. Another approach is vaccination. Like, there's already vaccines for like some bacteria, or what the bacteria may produce, like toxins or whatever, that already are in existence. However, developing vaccines can be problematic, and I will go over this in another video, but it's also not an easy thing. So that's why a lot of the focus will ultimately still be on antibiotics. So I wish I could end this on a higher note, but honestly, the future of antibiotics and bacteria is bleak, and it will get worse before it gets better, because we are at war. And honestly, we can't win this war, because the bacteria were here first, and they will keep on finding ways. Like, we'll develop a new method, they'll find a new way of countering it. So it literally is an arms race. It's just who can get the bigger gun, and we're just going to keep coming with bigger and bigger guns, and the bacteria will just keep finding a bigger and bigger shield to ultimately counter that. So it's an arms race that we cannot win. But the key thing is that we need to get back in the race, because right now the bacteria are getting bigger and bigger shields, and our guns are not getting any bigger. And right now, as I said, it's going to get worse before it gets better. So if anything I want you guys to get from this video is, remember, take antibiotics only as prescribed. Take them only when necessary, as determined by your doctor, and don't take them the full regimen. Don't throw them out, especially don't dump them down the drain, and make sure that bottle is empty. So as you can see, now that my shirt actually makes sense, but this isn't even my final form for all you DBZ fans, that's exactly the story with bacteria. It's like, they start here, Then they get stronger. Then they get stronger. Then they get stronger. So yeah, you haven't even seen their final form. And with that, Microman signing out. Along with Super Seed Facility.